Quantitative chemistry is a topic you covered back in year 11. It comes back in year 12 with a different set of calculations you need to be able to do. There are 4 main types of calculation you have to be able to get your head around in year 12 quantitative chemistry. The first section is on something called empirical formula. So in chemistry, there's actually 2 different ways of writing a formula of a chemical. The one you're most familiar with is molecular formula. The molecular formula shows you the actual number of each element in the compound. A different way of showing the formula is the empirical formula. The empirical formula is very similar to molecular formula, but it's like the simplest ratio of that formula. So if you can cancel molecular formula down to make it simpler, you do so. For example, let's say you had the formula C6H12. That would be the molecular formula of this compound because it tells you got 6 carbons and 12 hydrogens. The empirical formula of this same compound would be a cancelled down version of the molecular formula. C6H12 is the same as a 1:2 ratio of carbon to hydrogen, so you can write the empirical formula as CH2. So you're looking for the simplest whole number ratio of the atoms in the formula. Now what you might find in some cases is the molecular formula can be the same thing as the empirical formula if you aren't able to cancel molecular formula down. So in the second example, you got C3H8, 3:8 ratio. You can't make any simpler if you want the numbers to stay as whole numbers. So the empirical formula would be the same thing. It would also be C3H8. The only other thing we need to look at for empirical formula is a calculation you need to be able to do where you work out the empirical formula of a compound using mass values. It's easiest if we look at an example. This is what a question might look like. 128 grams of copper combines with oxygen to form an oxide. 144 grams of that oxide is formed. So we know in this case what the 2 elements are, so copper and oxygen are forming together, but we don't necessarily know in this question what the ratio is. It could be CuO, CuO2, Cu2O, etc, etc. So we're trying to find out the actual ratio to get the actual empirical formula. The calculation isn't actually that bad as long as you know how to lay it out. Basically, we're looking for the ratio between copper and oxygen. The first thing we want is the ratio between their masses. So I got 128 grams for the copper because that's mentioned very directly in the question. The mass of the oxygen that's added to the copper, you have to do a little bit of work for. The 144 grams is the mass of everything once it's all combined together. So the difference between the final mass and the initial mass of the copper must be how much oxygen which was added, which was 16 grams. Now once you've got the mass of each element, you want to convert that mass into moles by dividing by the RAM of each element using the mass number on the periodic table. So I've got 128 over 64 for copper gives me 2 moles, and 16 over 16 for oxygen gives me 1 mole. Now the ratio we've got here is the simplest ratio you could have for those elements, and that gives you the correct formula. We've got 2 coppers and 1 oxygen, so you give your answer as Cu2O. A couple of final points about how they make the question a little bit trickier. One thing they can do is give a very similar question to what we've just done, but instead of gram values for the questions, they give them as percentages. In that case, you don't panic. You're allowed to, in this particular case, treat a percentage value like a mass value in grams, because all you're saying is if you had 100 grams of a compound, the percentages would just be mass values out of 100 grams. The second thing that can make it a little bit harder is sometimes the ratio can be quite hard to get your head around. So in contrast, this first example is very clearly 2 moles to 1 mole. That's really easy to get the answer. But sometimes you get a decimal value for the mole, which can make it harder to see what the whole number ratio would actually be. Here's just a quick made up example. Let's say it was a ratio between element X and element Y, and this is the mole values we've worked out from this step of our calculation. It's quite hard to see directly what this ratio would be as a whole number. The strategy we can use using our calculator is if we spot which one of these numbers is the smallest number, in this case the 0.063, and we divide both of these numbers by that smaller number, that should give us actually a whole number ratio. So 0.063 divided by itself will just give you 1, 0.189 divided by the smaller number, the 0.063, gives you a whole number of 3. So our second section is on water of crystallization. Certain compounds in chemistry are quite attracted to water, and they will grab water from their surroundings and lock the water in to the crystal structure. So what we start with is a definition of what water of crystallization actually is, which is that it is water that is chemically bonded to the crystal structure. It's not the same thing as a compound being wet. It means the water's actually chemically combined into the structure. It's kind of trapped in there. Now, there's a very easy way to spot if a compound has got war of crystallization, basically looking for the dot followed by a number of H2Os. So in this example here we've got copper sulfate, that is a normal chemical compound, but copper sulfate is one of the compounds that does like to attract water to itself. This dot tells you that you've got war of crystallization, and the number afterwards tells you how many H2Os, how many waters there are per formula of the compound. So in other words, per copper sulfate there is 5 waters of crystallization attached to the copper sulfate. The number is sometimes referred to by a technical term. It's known as the degree of hydration. There's a couple of follow-up definitions. The word hydrated means a compound does contain water of crystallization. So for example, this is hydrated copper sulfate because you see the water of crystallization. If we dried out the copper sulfate, you can just heat it up and the water of crystallization does evaporate. It would become anhydrous copper sulfate. Anhydrous means it does not contain water of crystallization. There are 2 calculations you need to be able to do about water of crystallization. The first one's reasonably straightforward. It's to calculate the percentage of the water of crystallization. There's an equation you use for this one. The percentage of the water of crystallization equals the degree of hydration times by the RFM of water divided by the RFM of the compound times by 100. This equation maybe makes it look quite difficult. It's actually reasonably okay as a calculation. Let's look at an example. So here we've got tin chloride, SnCl2, with 2 waters of crystallization attached to it. Now the first thing I would do in this question is just straight away work out the RFM of the entire compound, because we'll need that for the bottom of our calculation here. Now for that RFM of the compound, you do include the water of crystallizations. You include everything you see here. And to get that number, you just need to use your mass numbers off the periodic table and count up your elements along the formula. That should give you 226 as the RFM. Now the RFM of H2O of water is also needed for this calculation. It's pretty straightforward to work out. There's 2 H's and 1 oxygen. That gives you a mass of 18. Again, we're just using mass numbers off the periodic table. So putting this all together, here's what the final sum looks like. The percentage of water of crystallization equals the degree of hydration, which is just the big number in front of the H2Os, so 2, times by the RFM of H2O, which in all cases will always be 18, divided by the RFM of the entire compound, so that's the whole formula here, 226, times by 100, in your calculator, 15.9%. The second calculation about water of crystallization you need to be able to do is to work out the value of the water of crystallization. In other words, you're going to be able to work out for a mystery compound what the big number in front of the H2O is for that compound. That involves you doing an experiment, which basically involves heating up a hydrated compound and seeing how much lighter it gets once you've got rid of all of the water. So here's an example. Let's say we had magnesium sulfate, but we don't know the water of crystallization attached to the magnesium sulfate. We might use an X here to represent an unknown number. Our strategy here is to put the magnesium sulfate with the water attached to it into an evaporating basin on top of a gauze tripod Bunsen burner and heat it so that the water of crystallization evaporates and the powder will get lighter. Basically, we heat it until we can no longer get it any lighter. So that would involve you heating it maybe for 5 minutes, letting it cool down and weighing it, repeating the process and seeing if it gets any lighter the second time round. You keep on heating it and weighing it until you get 2 masses which are identical, which shows you that you've got the maximum amount of water removed from the compound. That process is known as heating till constant mass. After the experiment, you'd have a number of values. You'd have the mass of your dish at the start before you added any powder, the mass of it after you added the hydrated magnesium sulfate, and the mass after you've heated up that dish with the magnesium sulfate and got rid of all the water to make it anhydrous. How we lay out this calculation to work out this mystery value of X is a little bit like empirical formula. We just want the ratio of magnesium sulfate to H2O. We start by working out their mass values compared to each other. So for magnesium sulfate, we've taken away the 12.73, the mass of the dish, away from the mass of the dish plus the anhydrous magnesium sulfate. At the end of the experiment, all you've got left is magnesium sulfate. There's no water here, so that's the best subtraction to work out just the mass of the magnesium sulfate by itself. For the water, we just want to work out how much lighter the magnesium sulfate got from the start of the experiment to the end of the experiment. 13.96 going down to 13.33. That drop has come about just because you've removed all the water from that compound. That tells you how much water was there in the first place, 0.63 grams. Just like we did for empirical formula, we got mass values. We want to convert them into mole values by dividing by the RFM of magnesium sulfate and separately H2O. That gets us mole values of 0.005 to 0.035. Now you may be able to work out the whole number ratio just by looking at this, but if in doubt, remember we can use the same strategy as before. Divide both numbers by a smaller number, this 0.005, in your calculator. That will give you the whole number ratio. In this case, it is just a 1 to 7 ratio. This means that there are 7 H2O molecules per magnesium sulfate. And that means we've worked out the value of X. X is just 7 for H2O. Now we've got two final calculations we need to look at, which are a little bit shorter and easier to do. The first of those two is atom economy. The atom economy is a calculation you can do to work out how efficient a chemical reaction is. To work out the percentage atom economy, you do the RFM of the desired product of a reaction divided by the total RFMs of all the compounds in that reaction, then times it by 100. Easiest if we work out an example. What they will give you is a chemical equation, which we got here, C plus 2H2O goes to CO2 plus 2H2, and it will give you some sort of indication about which of those products is the one you're trying to make. So it says here production of hydrogen, so we can assume that the H2 is the desired product. So to work out the percentage atom economy in this case, we take the RFM of the desired product, which is H2. H2's RFM is just 1 plus 1, which equals 2. Now, just being careful, we do need to multiply out by the balancing number, so that gives us 2 times 2 on the top. On the bottom of it, we've got the mass of all the products, so that includes the H2 again, but also with the CO2 beside it. The RFM of CO2 is 44, and we add on the 2 H2s that we had on the top of our fraction, so that goes in both places. We times that by 100, type it into our calculator, and that gives us our value. So the atom economy of this reaction is 8.3%. 8.3% is quite a low atom economy. It is good if your atom economy is high for your reaction. There are 3 main reasons why a high atom economy is good. The first thing is that it reduces the amount of waste produced over the course of your reaction. The second thing is that because you're producing less waste, you're preserving as much of the Earth's resources as possible so that it'll last for longer. And lastly, if you were doing this in a factory, a high atom economy is a more economical process because you're wasting less material. It's more cost effective as a process. The final section to look at is a section on calculating the concentrations of solutions. Concentration just gives you an indication of, in a solution, how much solid there is that's been dissolved in 1 decimeters cubed of the liquid, which is normally water. Now, decimeter cubed is a bit of an unusual volume value. A decimeter cubed is equivalent to a litre. Standard units for concentration are the number of moles per decimeters cubed, which gives us mole per decimeter cubed as our unit. The equation we use to calculate concentration values is concentration equals moles divided by volume. The one thing you have to be careful about here is volume must be in decimeters cubed for the calculation to work. If in a question they give you the volume in centimeters cubed, you will need to convert it into decimeters cubed. The way you do that is divide the volume in centimeters cubed by 1000. Let's finish with a couple of examples. First one here, quite simple. You're asked to calculate the concentration of 0.1 moles of sodium chloride in 200 centimeters cubed of solution. All I've done here is concentration equals moles over volume. The moles are given in the question directly. The volume is 200 centimeters cubed in the question. I've had to divide that by 1000 to get into decimeters cubed, the 0.2, and then it's good to go for the calculation. That gives me a final answer of 0.5 moles per decimeters cubed. You can be asked to work back the way. So if they give you the concentration and the volume, you could be asked to work out the number of moles in that volume. We just need to do a quick rearrangement of our calculation, or equation. So we get moles equals concentration times volume. And once again, I need to convert my volume in centimeters cubed into decimeters cubed. So 100 gets divided by 1000 to get me 0.1. Then it's just 0.2 times by 0.1 gives me 0.02 moles.